No, I don't. Okay, here we go. All right, we gotta go. Here's what we need you to do. I want you to find the domain for each of these. In fact, we'll just talk about it as a class right now because we're kind of pressed for time for today. So the first one, we'll just keep. What did I do? Boo. What? All right. Okay. Very good. All right. So fx. What type of a function is this first one that I've highlighted? Yeah, it's a linear function. Very good. Linear functions. Whenever you see a linear function, the domain is always going to be all real numbers. You don't even have to think about it. It's a beautiful gift from the linear function people. All right. What type of function is this one right here? 3x squared plus 2. Now, that's the name of the shape of the function. This is a quadratic function. Okay? Quadratic functions, according to that little activity we just did, have domains what? All real numbers as well. So if you're dealing with linear functions or you're dealing with quadratic functions, you're good to go with domains and saying that each of those are all real numbers because we've talked about it and explored them. However, this is a little bit different. This is our square root function. And this one we have to restrict the domain such that every x is greater than or equal to 0, simply because when we're looking for the domains, we're looking for the domains in the real number system, and we can't take the square root of a negative number in the real number system. So we have to start thinking about restrictions of domains. And then this last one here, what is the one thing, this is a rational, right? This is a rational function. And rational functions, you always need to be careful never to divide by 0. So is there a value out there in the world that if we plugged into this specific rational function, it would give us an output of 0 on the bottom? -3. Very good. So what we need to do is restrict the domain and say this is all real numbers x such that x cannot be a -3. Okay, now I've set you guys up perfectly for this one. And I'd like you to find the domain of this rational function, 1 over x squared minus 2x minus 3. Remember, we're going to have to get some factoring involved with this particular one. So we're going to factor the denominator. So I have a 1 over x squared minus 2x minus 3. So how does this factor? Anybody got it? X minus 3 and x plus 1. I'm sure we all could have done that. So that being the case, which two values would give me a 0 in the denominator? There's two of them. Yeah, 3 and -1. So in this case, we say the domain of this function here is all real numbers x such that x cannot be a 3 or a -1. Because if it was, we have a 0 on the denominator and g of x. So let's say we're given two functions and we know that they are functions, in fact, because they're defined to be. So we'll call them f of x and g of x. Well, we can do operations with functions much like we do operations with numbers. So what I mean by that is if I want to take f plus g of x, it's literally just f of x plus g of x. We're allowed to just, the sum of the functions, right, we're allowed to do that. No big deal. And in fact, we can do that with all of these. F minus g of x is literally just f of x minus g of x. What do you think f times g of x is? F of x times g of x, you got it. No big deal there. And what do you think f divided by g of x is? Very good. I heard f of x divided by a g of x, but what do you have to always be careful about here? So that g of x is not equal to 0. Okay, these are your basic function operations, and they work just like they work with numbers because functions behave so nicely. All right, so let's do an example together. And I'll give you some functions. Let's define f of x to be, how about 2x? And then g of x, we'll define it as 3x squared plus 1. What type of a function is f of x? Yep, sure can. It's linear, yeah. It is a linear function. What type of function is g of x? It's a quadratic. Very good. So what would f plus g of x look like? Yeah, it would literally mean f of x plus a g of x, which is just 2x plus a 3x squared plus 1. Cleaning this up a little bit, I get 3x squared plus 2x plus 1. So when I add a linear and a quadratic, I get a quadratic back. Oh, that's pretty good. That works out pretty well. All right, how is this different from this? What would f minus g of x be? Well, it would be f of x minus g of x, right? And that would be 2x minus, and notice I'm putting everything to the right-hand side of my negative sign in brackets so that you remember to distribute that, 3x squared plus 1. So that's my f of x minus g of x. When I simplify, I get 2x minus 3x squared minus 1. Cleaning it up, I get negative 3x squared plus 2x. Yeah, like on the actual tablet, it's a lot smoother. I don't know why. Okay, so let's give you two functions here. F of x is the square root of x plus 3, and g of x is the square root of x minus 2. All right, what I want to do is I want to add these together. All right, I want f plus g of x, and then I want the domain of f plus g of x. What's the domain of this going to be? That's the question that we're trying to answer. All right, well, the first thing we'll do is we'll add them together. So that's just the square root of x plus 3 plus the square root of x minus 2. All right, good. So I have my new function, and it's just the addition of the two functions together. But the question is, what's the domain of this new jointly added together function? Seth, what do you think, dude?
X so that x all real x's so that x is greater than -3.
Okay, so first let's investigate this one. We know the domain for f of x is all real x such that x is greater than or equal to -3. Is everybody okay with that part so far? Okay, good. What's the domain for g of x then, for this one over here? All real x such that x is greater than or equal to what? To 2. Okay, because I got to go to the right of 2. Now the way that we're doing that is we're looking underneath our radical, and we're setting that greater than equal to 0. So I just say x minus 2 greater than or equal to 0, so x must be greater than or equal to 2. That's how I got that right down there. Now if you consider this, if you consider these on the number line, here's 0, here's -3, and here's 2. The domain for f of x is all that stuff right there, right? It's greater than a -3. The domain for g of x is right there, all the stuff that's greater than 2. Well, where are they both covered? Greater than 2. So that is the joint domain for this one. All real numbers x such that x is greater than or equal to 2. No, you don't, but I think it's a really nice way to help you see why it's got to be greater than 2 or equal to 2. Because that's where they're both covered. Does that make sense? Okay, let's do this. Let's do function composition literally means that we take one function and we plug it inside of another function.
Is it the f and then it looks like fog?
Yes, exactly. So it looks like this, f
Or golf.
or goff, right? Yeah, that does not say fog of x, right? It looks like it, but it doesn't say fog. Nor does that literally mean to multiply the two, okay? This little like open circle here, this represents function composition. The way that we say this is we say f of g of x. That's how you read both of these, all right? And you have to realize that g of x is inside of f of x. So g of x is inside f of x. It's like a dream within a dream. It's crazy. You guys caught that? You guys caught that joke, huh? All right. Let me give you an example here. Let's say that f of x is equal to 2x. And let's say g of x is equal to 2x squared minus 3. The question then is, what is f of g of 1? F of g of 1. Please don't say fog 1. Fog 1. Fog 2. Sounds like a... Okay. So yeah, you got an answer. Awesome. So follow the logic here, right? So since this literally means f of g of x is inside of f of x. So we take the input, which is 1, and we run it through g of x. So follow with me. What's 1 squared? Yeah, so I figure out, so I want g of 1 is going to be 2 times 1 squared minus 3. So this gives me 1 times 2 is 2. 2 minus 3 is negative 1. You guys agree with that? Hello? Good. Then I take that negative 1, I run it through f of x. And I would get 2 times negative 1, so output would be a negative 2. So f of g of 1 would be a value of negative 2. Now, thank you. Is that the same thing as g of f of 1? 2 times negative 1 is negative 2. Is this the same thing, g of f of 1? Are those two things necessarily going to be the same? What do you think? Why not?
Because you get one first and then you plug it in.
Very good. You get 1 first, plug it in. So let's do this one together. Okay, this literally means g of f of 1. So first we're going to figure out what is f of 1. Well, that's just 2 times 1, which gives me a value of 2. Now that I have 2, I plug that into g, which is 2 times 2 squared minus 3. So that's 4. 4 times 2 is 8. 8 minus 3 is 5. So I get a 5 out of this. And those two things are not necessarily the same. Okay? So that's one thing that we're going to do with function composition when we plug one function into another function. The last and final thing, and I need all 11 of these minutes with you, is to talk about the domains of function composition. I realize that this is fast. We're going to practice this on Monday, all right? But I need you to get this information out to you before then. So, domain of function composition. Let's say I have f of x, which is equal to 2 over x minus 1. And let's say I have g of x, which is equal to 3 over x. And what I want, I'm going to leave some space here. I want to figure out the domain for f of g of x. So the composition. When I plug g into f, what's that domain going to be? So here's the logic, and see if you follow along here about how this works out. So I'm going to figure out, okay, first of all, my domain for g of x is all real numbers x such that x cannot be, what value am I not allowed to plug into g? A 0, right off the bat. Can't do that, right? And what's the individual domain for f of x? It'd be all real numbers x such that x is not allowed to be which number? 1. How come? Because either one of those two answers, right, depending on their domains, would give me a 0 in the denominator, and that's what I have to watch out for. So right away, since this is f of g of x, since g of x is inside of f of x, the very first number that I know cannot be plugged into the composition is which one? 0. Is 0. Very good. So I know right away this is all real numbers x such that x cannot be 0, because if I plugged a 0 into g of x, I would break the machine and it'd all fall apart because I'm not allowed to plug in a 0, right? Now, there is another number, and this is what I call the number in disguise, because it's a number that when you plug it into g of x, it becomes a 1. And a 1 is the one thing that we're not allowed to put into f of x. So you found it, and you know that that answer is 3. Okay, good. Now let's explain this. So this is my domain for my composite function. So what we have to do is we have to say, okay, we know that g of x is not allowed to produce a 1. How come? Because if g of x produces a 1, then a 1 travels on to f of x, and we're not allowed to plug a 1 into f of x. You guys follow me on this so far? So therefore, we must restrict g of x from producing a 1. So I just take whatever g of x is, it's 3 over x, and I say it can never be a 1. Because if it is, then I'm allowing it to go on to f of x, and I have to take into consideration the domain for f. What 3? This 3? This is what g of x is. This 3 over here. That's the answer it's going to be. That's the number in disguise.
If you put a 3 in g of x, then you get a 1 over there. And if the composition says that once you get that, then you put it in there. And if that's 1, then you put it over there. Then that would make a 0 in the denominator.
Correct. Correct. So that's how I did it, right? So I said 3 over x cannot be a 1. So I solved this little tiny equation over here. And I say that x can't be 3. So my answer is all real numbers x such that x can't be 0 or 3. What's interesting is that this number is not part of the composition, is it? Isn't that weird? How come you can plug a 1 into the composition?
Oh, because we put 1 into 3 over 1.
Very good, Seth. Because if I plug a 1 into my composition function, it goes through g first. If I plug a 1 into g, I get a 3 out. And then a 3 can be plugged into f.
So if it works for...
Minutes of class, okay? I have a composite function, f of g of x. I've been given 2 rational functions up top there. I have f of x is 4 over x plus 2, and g of x is 1 over x. The first thing you got to do is figure out the individual domains. So what's the individual domain for f of x? Yeah, x is not allowed to be negative 2. So far, so good? What's the individual domain for g of x? 0. Yeah, x is not allowed to be a 0. Now, since this is f of g of x, my domain will be all real numbers x such that x cannot be, what's the very first one we can't plug in there? It's going to be one of those two. Yeah, it can't be a 0 because g is inside of f, right? And now we need to prevent g of x is never allowed to be what value? What's it not allowed to be? You guys are giving me the answer. I'm asking you, what is g of x not allowed to be?
0.
Negative 2. G of x is not allowed to produce a negative 2. Okay? So I set whatever g of x is, 1 over x, it's not allowed to be a negative 2. Because if it was, whatever number I plug in there, it would run into a domain error for f. So it's never allowed to be that. So what value, when I solve this little equation here, I'd get 1 over negative 2 is not allowed to be x. Oh, look, there's the other answer. X is not allowed to be negative 1/2. Notice that this value, though, negative 2 is allowed in the composite function because it has to pass through g first. And when you plug in a negative 2 to g, you get out